can determine forces in motion situations where our system moves with constant velocity. As we know from Newton's second law, constant velocity motion means that the total force on the object is zero. This condition is often referred to as equilibrium. If, in a particular case, the constant velocity is equal to the zero vector, then the system is static, meaning it's motionless, and we refer to the system as being in static equilibrium. If, however, we have a case where the system moves with constant non-zero velocity, then we refer to the system as being in dynamic equilibrium. It's important to remember that while to our eye, a static equilibrium case looks quite different from a dynamic equilibrium case, both cases share the key similarity that the velocity is constant and therefore F net is zero in both cases. This means that the procedures for finding forces will be very similar for both cases. Let's discuss this by looking at the following setting. Imagine we're pulling on a rope attached to a box of mass m equals 40 kilograms, sitting on level ground. The rope makes an angle of theta equals 35 degrees with respect to the horizontal, as shown. The coefficients of friction between the box and the ground are static coefficient equals 0.25, kinetic coefficient equals 0.2. The box is motionless. What are the contact forces, expressed as vectors, acting on the box? Let's employ our key steps for finding these unknown forces starting from motion observations. The first two steps, identify the system and observe system motion to determine the total interactions, F net, go pretty quickly here. We're clearly focusing on the box, so that's our choice for the system. And, as we discussed, we have a case here of constant velocity equals zero, that is, static equilibrium. So we know the total interactions F net are also equal to zero. The next key step requires more discussion and care. We need to identify specific forces on the system that contribute to F net. In doing this, we need to make sure we don't neglect any significant interactions, so we'll be systematic about this. Let's construct our list of agents that can exert forces on our system. First, let's start with all agents that exert contact forces on our system. We'll look for those agents in the surroundings that cross the system boundary and make physical contact with our system. There are two such agents, the rope and the floor. With the rope, we can identify a tension force we'll label as F sub t, and with the floor, we can identify a surface contact force we'll call F sub f. We now look for agents in the surroundings that can exert forces at a distance. In this case, we have one such agent, the Earth, which exerts a weight force. That's it. We have three significant interactions expressed as forces acting on our system, and, moreover, we know that the net force is the vector sum of these three. In fact, here we already know what F net must be because in the previous steps we noted that our observation of constant zero velocity means F net is zero, so the sum of these three forces must also be zero. Let's use a free body diagram to help us compactly summarize and visualize all this. Starting with the dot to represent our system, the box, we know that we can represent the tension force with an arrow that points along the rope away from the system. Since we know the angle the rope makes with the horizontal, the tension force must also point at the same angle, so we can draw that in. The weight force acts downward, so we can draw that in too. The floor force is a bit more challenging. How would we draw an arrow to represent the force of the floor acting on the system? Give this a try and see what you come up with. Here's the correct way to draw the arrow to represent the floor force. We know how to do this because the sum of all forces must add to the zero vector. So, graphically, if we sketch in the tension force and the weight force, then the floor force must be such that when we add all three forces, the total yields the zero vector. At this point, let's specify a coordinate system and represent these vectors in component form. Let's choose the horizontal axis to be the x-axis, positive to the right, and the vertical axis we'll choose to be the y-axis, positive upward. From this diagram, we can now write out explicitly our interactions in component form. First, the weight force. The weight force has one non-zero component in the y direction, so we can write the weight force in component form like this. From the diagram, we see that the tension force will have non-zero x and y components, so let's represent the tension force like this. Similarly, the floor contact force has non-zero x and y components. Let's represent the floor force like this, where F is the component parallel to the floor. This is the friction. And N is the component perpendicular to the floor. This is the normal force. We emphasize here all the symbols we write, W sub y, F sub tx, F sub ty, F, N, represent components and could be positive or negative. We'll figure out the signs of these components during the final step, solving for unknown quantities. Let's do that now, applying Newton's second law with all the vectors in component form. From this vector expression, each non-zero component corresponds to an equation, meaning F net equals the zero vector corresponds to each component of F net must also sum to zero. To solve for unknown forces, we need to have as many equations as unknowns. Here we have 2 equations and 5 unknowns, so we need more information to make any progress. Let's start with the weight force. We're given the system mass, so we know that the magnitude of the weight force is m times g, and the direction is downward, so W sub y must be equal to minus mg. We can also simplify the components of the tension force. From our free body diagram, we see that both F sub tx and F sub ty must be positive for our choice of coordinate system. Moreover, the magnitudes of F sub tx and F sub ty are related to the magnitude of F sub t by trigonometry. So we can insert this information in our expressions, and we now have 3 unknowns, the components F and N, as well as the magnitude of the tension force. So, are we stuck, or can we make any more simplifications? Let's address each of these answer options. First, setting the magnitude of the normal component of the floor force equal to mg is incorrect, because there are 3 forces that have non-zero components in the y direction: the weight, the normal component of the floor force, and the y component of the tension force. So saying that the magnitude of the normal force is equal to mg would mean that the magnitude of the tension force would have to be 0. That happens only if we're not pulling on the rope. We assume that we have a non-zero pull, so that means the magnitude of the normal force cannot be equal to the magnitude of the weight force. The sliding friction model using mu sub k doesn't apply here because the object has to be moving for this model. Here the object is motionless. Now you may have selected the static friction model to relate the magnitude of the normal force to the magnitude of the friction. Actually, this would only apply in a very special static case, the case where the object was just on the verge of moving. We did not make that assumption, so we do need more information to proceed. So, let's provide that information by making the assumption that the object is on the verge of moving. In that case, we can use our static friction expression in the x equation to express the friction component in terms of the magnitude of the normal component of the floor force, where, from our diagram, we put in explicitly the direction of the friction, which points in the minus x direction. We can now solve this to obtain an expression for the magnitude of the normal force, which we then can use in the y equation, where we see from the diagram that the normal component is positive, so we can put that in explicitly. We now can solve for the magnitude of the tension force, where, after we plug in all the numerical values, we find it here. Now using the angle theta, we can find F sub t, the tension force, in component form. With this in hand, we can now solve for the magnitude of the normal force, and then we can finally solve for the magnitude of the friction. We put in all the correct signs, so now we have the force of the floor on the system, the box, in component form. And so, starting from the motion observation of constant zero velocity, static equilibrium, we have shown how to solve for the contact forces in this particular case. We can turn this problem into one of dynamic equilibrium. Let's start from the top with the same assumptions, except now we state that from the start, the box is moving in the plus x direction at constant speed. How would we find the contact forces? Because we have a case of constant velocity, we still have equilibrium, where F net is equal to 0. We would still identify the same agents and forces. However, our model for relating the magnitudes of the floor force components would now be different. We would now use a sliding friction model. So, although we would use nearly all the same steps as for the static case, we would expect the quantitative results might differ. We won't discuss that case in detail here. Instead, we encourage you to go ahead and work out the dynamic equilibrium case on your own and discuss that in the forum. In the next lecture, we will turn our attention to finding forces from motion observations in cases where the velocity is not constant, meaning cases where we know F net is not 0.